Hi everybody, I'm Clara and I work in EDF R&D, and the topic of our talk is the new Code Aster's HPC capabilities, and we will highlight some points through industrial applications. So here's the overview. I'm going to start with a quick word on numerical simulation in EDF, and then we will highlight some industrial illustrations before drawing some conclusions. I think you know EDF, it's one of the largest utilities in the world, and we operate different kinds of assets, and there is a common point between all these assets. It's their long-time operation. For instance, it's 25 years for the wind turbines and the solar panel. It's 60 years for the nuclear power plant, and it can reach 100 years for the dams. And in order to asset the safety of all this installation, we easily rely on numerical simulation. And if you look back on numerical, if you give a focus on the numerical domain, we study the integrity of the containment building, for instance, the vibration of the primary circuit, the vibration of the turbines, and we also and we have a focus also on the nuclear waste storage that Clara will talk about. And this is I'm just regarding this installation with my solid engineer's eyes, so solid engineer eyes, but you also have lots of topics in electromagnetics and fluid dynamics. And all the studies, they all rely on numerical simulation. And there is a long story of numerical simulation in EDF. It began in the 60s. In fact, it began with the finite elements analysis. And at this time, there were lots of different tools, one for 2D, one for 3D, one for model analysis, one for nonlinear analysis. And in the late 80s, the decision was taken to have one unique finite element software, and it was the birth of Code Aster. And I will mention one special date. It was in 2001, where Code Aster was released as an open source software, so this is why we are all here. And I will also highlight 2020, when we heavily redesigned Code Aster to make it HPC ready, and this is what we are talking about right now. So here is a picture of the primary circuit of a nuclear power plant. You have the heavy component, and you have here the pressure vessel, which is the heaviest component of the primary circuit. And we want to assess the effect of a hypothetic crack here on this pipe that go out of the pressure vessel. And to do that, we use a nonlinear simulation, and it's a thermomechanical problem. So I'm going to describe this staggered study that we run. And first, it begins with a thermal problem that we solve on the P1 finite element problem. And then once we have the temperature field on the P1 element, we project it on the quadratic mesh in order to ensure the stability of the thermal deformation field. And then we inject this deformation in the mechanical problem, which is solved on this quadratic mesh. We use a nonlinear constitutive law. It's a von Mises plasticity, where every parameter depends on plasticity, on temperature. Sorry. So it's a highly nonlinear problem, and until recently we use direct solver. They are very robust, but they are very expensive in time and space. You need lots of memory and lots of time to get the solution. We have also experienced algebraic multigrid preconditioners, which are known to be very efficient on lots of problems, but on this particular problem, they were not efficient at all. So we tried to implement a new preconditioner. It's a domain decomposition preconditioner, which is based on the theory which is called GNEO, which was discovered by a French researcher, Nicolas. This preconditioner was also implemented in a library called HPGDM, which is also developed by a French researcher. And this library is also available in HPC. And we have a very tight connection with HPC in Code Aster, and so we implemented quite easily this new preconditioner. And here is a focus. So this is the solution of a linearized system. You linearize the residual, and you have to solve this linearized system. And this is the decrease of the linear residual, thanks to the iteration of the solver. And here you have the decrease when you use Boomer AMJ, which is a very well-known algebraic multigrid preconditioner. And here the solution with HPDDM. So you see how fast the convergence was. And what could be done with that? We could solve the problem with more than 1 million degrees of freedom. We did something like 50 time steps, and the problem was run on something like 2,000 subdomains. You have here the domain decomposition of the domain, and the solution was obtained in 25 hours of computation.
Hello. So hello everybody. I'm Clara Ordonez, and I'm going to be presenting to you another industrial application. So the CGO project. So the CGO project is France's deep repository for its nuclear waste. So more specifically, it's high and intermediate level of radioactivity waste. So in the CGO project, they are going to excavate galleries 500 meters deep into the ground, and they have to secure that site for hundreds of thousands of years. We come into play because there is a need for simulation in the gallery crossing that cannot be solved with 2D simulations, and that have a specific effort localization that requires some specific mesh refinement, okay? So that results in huge matrices, very coupled, that need to be solved thousands of time steps, and we need so extremely scalable and robust methods. Okay, so in order to solve these types of problems, 2 PhD were done. So 6 years ago, we started my PhD. We started with a simplified problem. So we worked with the saturated thermohydromechanics problems. So we have the linear momentum equations for the mechanics. We have the water mass conservation for the pressure of the water, so infiltrating in the clay. And we have the energy conservation for the temperature of the nuclear waste. And so I'm not going to go into a lot of details, but for these simplified problems, we proposed a block-Gauss-Seidel type preconditioner based on these physics type blocks that we can see there. So the displacement, the pressure, and the temperature. And we proposed this block-Gauss-Seidel preconditioner with nested iterative methods that heavily relies on these algebraic multigrids that are highly scalable. And then we ran a scalability study on a simplified problem, so a meshed cube to start, to which we applied some pressure and some temperature. So there you have the reference for where we go into detail on the scalability study, but I'm going to show you some quick results. So we have the weak scalability. The weak scalability is when we choose a number of degrees of freedom per CPU, and then we're going to increase the problem by increasing the numbers of CPUs. So we choose 1 million degrees of freedom per CPU. If we want to solve a problem of 10 million degrees of freedom problem, we need 10 CPUs, 20 million degrees of freedom, 20 CPUs, and as such, right? So here you see that we increase the problem by increasing the CPUs, and we have the time to solution, the ratio with the first resolution. So I'm going to talk only about the green line. Here we start with a 20 million degrees of freedom problem, and we're going to increase the size of the problem until we reach 1.2 billion degrees of freedom. So we multiply the size of the problem by 60, and we see that the time is only multiplied by a little bit less than 2. So these were excellent results because we heavily rely on these scalable methods, right? So algebraic multigrids. We were happy. Nevertheless, it was a simplified problem, so a cube. So we tested these methods on a real-life industrial simulation with complete excavation and consolidation methodology with multiple time steps, and we were using Drucker-Prager with positive hardening, so we were no longer in linear elasticity. So for this real-life simulation, the problem reached more than 300 million degrees of freedom. We used more than 2,500 CPUs, and the solving time was a little bit less than an hour and a half. Okay, we were very happy for two reasons. So one, these types of we couldn't solve these type of problems with the previous methods. It was just not possible. And second, it is a great time-wise result, because in 1 hour and a half, that's not very long, okay? The next step, so this was still a very simplified problem. The real-life problem is unsaturated, and so we needed a second PhD. This is Mehdi's Etauchi's PhD. He worked in these unsaturated problems, which brings a lot of more nonlinearities, okay? So he has the linear momentum balance, so the mechanics equation. He has the water mass conservation, so for the pressure of the water, and you add this diffusion of a gas in the porous medium, and so you have the hydrogen mass conservation. Okay, so this is his type of problem. Here you see the injection of hydrogen on a porous medium over 1 million years, and you're going to see how the gas saturation increases and decreases normally. Yeah, so yeah, you see that it increases. So this brings a lot more non-linearities. So the methods that he proposed are based on nonlinear domain decomposition. So he uses restricted additive Schwarz preconditioned exact Newton, so Raspen. So this is an excellent method because it inherits the parallel nature, so it's highly scalable. And he works with the global system, okay, not as previously where we worked with kind of physics-based blocks. Some of his original contributions are the proof of the extension of the Bayesian of attraction compared to the classical Newton methods, and new algebraic SVD-based coarse problems. So he has a lot of results. If you're interested, you have the references here below. And I'm going to show you some of very simple simulation, but he has done a lot more complicated ones. So here he ran some multiple simulations with various time steps with multiple ending of years. Okay, so a little bit less than a year, and he augmented the time until he reached 500 years. And he compared the time of Raspen to solution to a classical Newton method. The first great result here is that you can see that the speed up of Raspen is better overall. And if I'm going to concentrate of his 500-year simulation, you can see that Raspen took 5 times less time in order to solve the problem than the classical Newton. So we're very happy with the result of Mehdi, but more importantly, he solved a much bigger problems. And even though these methods were developed for the CGO project and these unsaturated hydromechanics problems, they were also tested on various different problems with very promising results. So we are very eager to see what turns out of these methods.
here are the conclusions. So Code Aster is what we call the legacy code in the community of finite element solvers. So it's an old solver, 89. But we have been rewriting and redesigning it for years, and the last redesign for HPC came with many difficulties. We had to change the architecture of the solver, of course. We had to rethink the algorithm because everything is distributed, so you have to think parallel and you have to think scalable, as Clara told it. When you have millions or even billions of degrees of freedom, your algorithm you must be linear. It can be different. And we also had a lot of work on the linear algebra because you have to solve these huge linear systems. And as you see, we can get some nice performances. And so I would like to congratulate the development team because the job is really great. And we can now solve an unimaginable simulation now. And we also think that this is a game changer for the application and for numerical simulation in EDF. Okay, thank you for your attention.
Hello, I have a question for Nicolas on the first part of the presentation. Is it useful to have a small mesh, or does it was for the test, for the rupture case, for your rupture case? So do you have better results when you refine so much the mesh?
The fact is, before these new capabilities, when the engineers were designing their mesh, they were thinking in terms of size of the problem. They were thinking, I must have 1 million degrees of freedom. Above, I cannot solve it. So, and if you refine the mesh, you see that the results still change. So perhaps you do not need 100 million degrees of freedom, but you need a much finer mesh than 1 million degrees of freedom.
Okay, so in your case, you spend less time. The user consumes less time because it doesn't have to think about to refine some part of the geometry and to unrefine some other parts that are not okay.
Yeah, I am quite sure that we do sometimes simulation where the mesh is not converged.
Okay.
That's my point.
Thank you very much. My question is about the HPC Aster code is depend of kind of software for computation.
Can you do it again, please?
En fait, est-ce que ça dépend de certains systèmes d'exploitation? L'installation de la performance de la HPC.
All those simulations, they are run on our cluster. But and if you want to reach those sizes, I mean billion of degrees of freedom, you need a supercomputer. You need a cluster, yes, of course. But yes, you can also. I run parallel simulation on my laptop, and I gain time. So no, you must have a Linux computer. That's all.
Okay, but you need some application depend, or is any application Debian or Red Hat, etc., etc.
I don't think so.
Okay, because now in IRSN we don't have problem about Red Hat version and compatibility in HPC Aster code.
Okay, perhaps I cannot answer the question. I think that the operating system on our cluster is a Red Hat.
I would like to know in which version of Code Aster we could find this development.
The actual version of Code Aster.
Okay.
The first HPC capabilities, I think, were introduced in the 17th version.